Okay, in this last notebook for statistical thinking, we're going to go over continuous variables. So a continuous variable is not discrete. So in the last one, basically went over discrete variables. It's either like yes or no, or something like that, basically. It's just a discrete variable. So a continuous variable is just any number, okay? So the way that we're going to do this, and actually let's actually use this example here of the speed of light experiment, okay? So Michelson, this guy, he was a scientist, and he wanted to figure out, well, what is the speed of light? And so, in physics, they say, oh, the speed of light is this, right? Well, he said, well, I actually don't think that these are necessarily maybe accurate, right? Because just because you measured it once doesn't mean that that's right, right? So he did many different experiments, and he got different results. So 299.85, 299.74, 300.07, 299.83, etc. And these are all in megameters per second. And he said, well, I don't think that these are actually all accurate either, right? They're not perfect because things like temperature, dew point, his instruments, and etc. could have actually impacted the results. So what we can do is we can use some continuous variable measurement, something called the probability density function, to kind of estimate what the average is, okay? And so this probability density function is a lot like a histogram, but it's actually more like a probability mass function that's used for discrete variables. So this shows the likelihood of observing a value, a value of a continuous variable, okay? So let's actually represent how to use this, okay? So this curve represents a hypothetical profit and loss probability density function, okay? The mean is 1 and the standard deviation is 1, but the fatter tails has fatter tails than a normal distribution. The 5% var point is 1.82 standard deviations below the mean versus 1.64 for a normal distribution. So basically this curve is not exactly normal, okay? The area to the left of this line here is our value at risk, okay? So if you're not a finance person, you can kind of ignore some of these concepts, but basically we have a 5% probability of our actual circumstance being lower than our risk point here, okay? And that basically means you have a 95% probability of it being above, okay? So a probability density function is really useful because it allows you to guess or assume when something will actually happen. So let's look at it with buses, okay? So what's the probability that the bus will arrive in less than 30 minutes? Well, that basically is equal to this graph right here. So we have 30 minutes is here, and we're going to shade anything to the left of that, so left less than that, and we're going to measure the area under the curve here, okay? And that will tell us the probability here, the probability density, that the bus will arrive in less than 30 minutes. Now, we don't need to do calculus, but this is the way you would actually do it using an integral. We can actually just measure it, which is nice, using simulation. So no calculus required for this, but we will actually be measuring the area under the curve. And you can actually look at the cumulative distribution function as well, and you can actually check here 50 and 30. So you can actually see that this here is the same way, okay? So either a histogram or a CDF will really give you the same thing, okay? So let's actually look at a normal distribution, and we should actually really declare what a normal distribution is. A normal distribution is where the median is, and the curve looks something like this. The median, one standard deviation away from the median, contains roughly 68.3% of the data. 2 standard deviations away from the median contains roughly 95.4% of the data, and 3 standard deviations away from the mean, have I been saying median? Mean, always mean, is 99.7% of your data. Now, how do you actually know if something is normal or not? Well, there is actually kind of some statistical tests you can use, but honestly, it's easier to simulate it. So let's just go over some examples to kind of give some ideas here. First, what we're going to do is we're going to create 3 different normal distributions. One with a standard deviation of 1, one with a standard deviation of 2, and one with a standard deviation of 3. Okay? And again, actually I should show you what the documentation is for this. And we can see that the first number is the log, which is the the center, the mean, okay? And then these are the standard deviations, and then this is our sample size. So we'll just go ahead and do that. And then we're going to actually plot each of those histograms. And you can see that these are the histograms of each. So you can see this is the blue is standard deviation of 1, red is standard deviation of 3, and yellow is standard deviation of 10. Now, if I were to show you the first one, and I said, is this a normal curve? You might say it's very pointy, right? Well, that's true, but the trick is that it depends on your scale, right? All normal distributions don't necessarily look like this unless you're zooming in on them correctly, right? So this is something to keep in mind. Now, we can actually make an ECDF, which is a better way to actually check for normality as well. So we're going to make a little function here that just creates an ECDF for us, because in the previous notebooks we kept doing it by hand, but now we can actually make it a function so that we don't have to do it. So we'll go ahead and make that. And then we're going to make 3 different ECDFs. We're going to use these samples that we created before from a normal distribution, okay? And we're going to do this. And now we're going to plot each ECDF, okay? So we can see here we have a standard deviation of 1, 3, and 10, and these are the ECDFs for each, okay? Now remember, these are all in fact normal distributions because we plotted them using a normal distribution function. So we do know that these are all in fact normal. Now, it's important to remember though that normal distributions, there are some caveats here, okay? Normal distributions are probably the most commonly used distribution type. Also, they're the most common one used in pretty much everywhere, in statistics and modeling, financial modeling. Often, though, the data is assumed to be normal, and then you're going to use a normal distribution. But it's important to know, though, that it might actually not be normal, right? You actually want to check these. So what we can do is we can check the normality of this, okay? So we can just say, okay, we're going to look at a data set, and we're going to say, is this a normal data set, yes or no? Okay. So I'm going to read this data set in. We're going to say, okay, this is called Belmont Stakes. So the Belmont Stakes is a horse race, and the data set contains the number of seconds it took to win the race for each of these races. So there's 89 races here, and this was the winning race, okay? The winning horse, how long it took. And you can see that some are shorter and some are longer, okay? So yeah, okay? Then what we're going to do is we're going to calculate the mean and the standard deviation. So the mean finishing time, or the winning time, was 149.22 seconds, and the standard deviation was 1.61 seconds. So what we'll do is we'll create a normal distribution using those mean and standard deviation, okay? Then what we'll do is we'll actually create our kind of observed samples. So we'll actually look at our samples that this is our theoretical one. So this is our theoretical one here, which is based on our mean and standard deviation. And we're going to say, based on our mean and standard deviation, what should a normal distribution look like? Then we're going to actually measure take our actual data, and we're going to create an ECDF for that. Then we'll just plot them, okay? And we can see here, and I'll zoom out a little bit so we can see the whole graph. We can see the ECDF of our actual data is in blue, and the ECDF of our sample data is in red. Remember, the red data is what would theoretically be a perfect normal distribution, and the blue data is what our actual data is. So what does it look like? Does it look normal? It's pretty close, right? And this is a really good way to test whether something is a normal distribution or not. You can see here that there are some outliers here, and there's some outliers over here. So the tails of our distribution here may not be perfect, but it certainly looks like, generally speaking, it's a normal distribution. So let's actually ask another question here. What's the probability that another horse will run as fast as Secretariat? Secretariat is a very famous horse that ran the Belmont Stakes in 144 seconds. Basically, it's the fastest time that we have on record. So, what's the probability that another horse will run as fast as Secretariat using the data that we have? What we can do is we can actually create a sample of, let's see, 1 million. We're going to basically do 1 million races with a mean and standard deviation using a normal distribution, okay? And because now we know that it's normally distributed, we can now simulate from that. And we can say, well, we can actually assume things based on that. So we can say, calculate the fraction of the results that are equal to or less than 144. So we're going to take whatever is less than our whatever the seconds is less than or equal to 144, and we're going to measure that from our samples, and we'll divide that by the length multiplied by 100. And that will give us the probability, okay? So the probability that a horse will get the same time or faster than Secretariat is 0.06%. So it turns out that Secretariat was a very remarkable horse, in fact, very unusual. So it's very unlikely that we'll see that anytime soon, but it's possible. Okay, let's look at an exponential distribution. So an exponential distribution is like a Poisson process, which we looked at in the last notebook, where the two events are independent from each other, but they're actually looking at the waiting time, okay? So when you have multiple Poisson processes put together, that actually creates an exponential distribution, okay? So an example would be like nuclear incidents. So how often, what's the waiting time between two nuclear accidents happening? That is Poisson, that is an exponentially distributed thing. The individual event, the probability of the individual event happening is a Poisson process, okay? However, if I want to measure the time between two Poisson processes, that's an exponential distribution, okay? So that's the difference there. So this function calculates the waiting time of the two successive Poisson processes, okay? Remember that the time between Poisson events is exponentially distributed, okay? So what we're going to do is now we're going to use this exponential method, and we're going to say 20, okay? This is the amount, basically the average amount of time that we wait between nuclear incidents. We'll just call it 20 years, okay? We don't really know, we'll just call it 20 years. And we'll do a sample size of 100,000. So then we'll actually simulate that rather. And then what we'll do is we'll make a probability density function. So you can say the total waiting time in years and a probability for that, okay? And then we can actually okay, so let's actually interpret this PDF, okay? So here is, I guess, 25. So the probability that we have to wait 25 years or less, basically, or just basically the probability that we're going to wait 25 years is about, let's see, is this in 20? Oh yeah, this is in waiting time, and then the PDF is the Y label is, I guess it's in percentages, okay? So, or it's in decimal percent. So it's going to be about 1.5%, or 10% rather. No, that's right, 1.5%. Pretty unlikely, I guess. So 1.5% that we'll have to wait a certain amount. Now, what we can do though is say that anything to the left of this, okay? So the probability that we'll have to wait 25 years or less, you can actually sum up this area, okay? So it will be like all of these points summed, okay? Basically the area under the curve, which might end up being something like 10% or something like that. We can actually measure that, okay? So you could just count basically the number of times below or above a certain point and then divide by the total, and that would give you the total probability, okay? So that's how you would actually do an exponential distribution and measure it. Now remember, an exponential distribution is the waiting time between Poisson processes, whereas if you're trying to calculate an individual event happening, that's a Poisson distribution, okay? All right, Poisson process. Okay, so we can actually then say, okay, what about multiple successive processes happening? So for example, we could use something from baseball, okay? So we're going to model the waiting time to observe a no-hitter and the hitting of a cycle, okay? A no-hitter is basically where, if you know anything about baseball, is where the pitcher pitches every ball in the game and no one hits the ball, the batter doesn't hit the ball. So basically the pitcher is doing a very good job and no one hits the ball the entire game, okay? They never get to a base. The mean waiting time is 764 games. It's very uncommon. The mean waiting time for a cycle is 715 games, okay? So what's the waiting time between a no-hitter and then a cycle? Okay, that's basically what this would be. It's kind of an unusual thing that you'd want to measure, but you could do that. So you can actually use this function right here. This is kind of an extra thing that's not really super useful in this particular class, but it's kind of just to give you an illustration. And we can actually measure the waiting times between these two things. And you can see that we're in thousands of games now because it's very, very uncommon. We have a 0.05% chance of waiting basically 1,000 games. Okay, it's very, very unlikely. We could then make an ECDF where you can see that I have an 80%, basically after about 2,100 games, I have an 80% chance of seeing that happening. Okay. But it's very uncommon though, right? So that's basically what that means. Okay, so that's this notebook, and I went over mostly exponential distributions and also checking for normality because and making an ECDF. Those are all important. So these are good things that you can check in your own work and apply. This is a more advanced week, and that's why we're putting it at the very end of the semester. But it's definitely important, and it's something to pay attention to. And if you have any questions about it, please feel free to ask me.